Hi everyone, my name is Saif. Welcome back to a new video of modeling and simulation of power system component video series. In this video, we are going to simulate the power factor correction in a single and three-phase simple circuits. So let's start with an example. If we have a load which draws 100 kilowatt of active power and 100 kilovar of reactive power, which means that it consumes 100 kilowatt ampere, the power factor of that load will be the ratio between the active power to the apparent power. Now, for a certain reason, if that load starts consuming less reactive power, so it's 33 kilovar instead of 100, the apparent power will be reduced as well. In this case, the power factor, which is the ratio of the active power to the apparent power, will increase. So we start with a power factor of 0.7 or 70%. We end up with 0.95 or 95%. Now this device or load is on inductive load. Now one way to reduce the reactive power is to introduce a capacitive or a simple capacitor. Therefore the total reactive power will be reduced, which means on improvement in the power factor. This process may be referred to as power factor correction. Now the power factor is an indicator. As I mentioned, it's the ratio between the active power to the apparent power. Sometimes it's also called displacement power factor. Other types of power factor is basically out of the scope of this simple video. Now a low power factor can be problematic. One of the solutions is a reactive power compensation, and that can be done by introducing capacitors or other means to improve or correct the power factor. Plenty of benefits of improving or correcting the power factor. One of them is to increasing load capacity of the existing circuits. Basically, less apparent power means less drawn current, and therefore there will be an extra room for extra load to be connected, and therefore increasing the loading capacity. Now we know that the power losses are proportional to the square of the current, and when we improve the power factor, we will reduce the current and therefore reduce the power losses. Now when we reduce the current, the voltage drop will be reduced, and therefore an improvement in voltage profile for that load or the loads connected to the same source will be presented. Now we can correct the power factor using different methods, but in this presentation we're going to simulate the correction of power factor in a simple single phase circuit, and we also introduce simulation of capacitor placement in a three-phase circuits to improve the power factor. Of course, we will introduce the calculation behind choosing the size of the capacitors. So let's start with simple mathematics. Basically, in alternating current, the apparent power is a production of voltage multiplied by the current, and the active and reactive power are calculated accordingly. Now the power factor, as we said, is the ratio between the active and apparent power, but it's also the cosine of theta, and theta is the angle between the current and voltage. So far these are calculations for a single phase. For a three-phase, the calculations are similar, and in this case the power factor of a three-phase will be the ratio between the active power of all three phases to the apparent power of all three phases. Now we'll start with correcting the power factor in a single phase circuits. So a very simple resistance and inductance circuit or load. We will introduce the capacitor, and in the next slide I'm going to present the calculations, find or to size the capacitor, but basically these are the values that will be used in the simulation. Alright, so first, giving the voltage and the impedance of that load, we can calculate the current drawn by that load, and you can already see that theta is close to 90 degrees, which means that the power factor is very low. Knowing that the power factor is cosine theta, the apparent power which is the voltage multiplied by the current conjugate, equals to 398 volt ampere, and that can be written in terms of the active and reactive power. The power factor, as we mentioned earlier, is a ratio between the active power to the apparent power, or its cosine theta, which is 0.1. Now there is two ways to correct that power factor to unity. Basically, we can equalize the inductive reactive power drawn by the inductor by introducing an equal capacitive load as a capacitor connected in parallel, and therefore the total reactive power will equal 0, and the apparent power will in this case equal to the active power. Or we can push the imaginary part of the current, which is in this case 1.98. We can push that value to 0. The current in this case will have only the active component. So we have to calculate or size the capacitor based on two methods. First method is to equalize the reactive power drawn by the inductor using a capacitor. So the capacitor reactive power will be 396 volt ampere reactive, and from that value we can find the value of the capacitor using the voltage applied to the circuit, and that value will be 31.5 microfarad. If we use the current, and in this case we are trying to push the imaginary part to 0, and again using the voltage, we find that the impedance of the capacitor will be 101 ohm, or the capacitor value will be 31 microfarad. I won't go in details here because I'm going to build it. So for the three-phase circuit, 3 phases with different loads, so it's an imbalance. The parameters or values of the circuit are presented in table number 2. Now, in order to calculate or size the capacitors associated with phase B and phase A, since phase C is a resistive load, doesn't require any adjustment. For phase A, we start with the current, trying to find the current, especially the imaginary part of the current, trying to find the angle between the voltage and the current, and then we can calculate the reactive power of phase A. We also can use the active and reactive power to calculate the power factor. We are interested in finding the reactive power in order to equalize that value with a capacitor or a capacitive load. So for phase B, we also find the current, theta, and hence the power factor at phase B. At phase C, we already know that it's a resistive load, so there is no phase difference between the voltage and current. They are in phase, and the power factor is 1, or unity. Now the procedure is repeated here. For phase A, we can find the capacitor size by assuming that the capacitor reactive power will be equal to the existing load reactive power, which is 2000 volt ampere reactive, and from that value through the voltage we can find the capacitor size required to push the power factor of phase A to unity. Or we can use the imaginary part of the current, which is 8.3 ampere, in order to find the capacitor size. Now for phase B, the reactive power required is 500 volt ampere, and the capacitor will be smaller than the required in phase A. It's only 27 microfarad. The same value we can obtain by pushing the imaginary part of the current flowing through phase B to 0. The circuit is simple. References cited early in this presentation are presented here. Let's go to MATLAB. I've already started MATLAB. We can start Simulink by either writing Simulink in the command window or just press Simulink button and then a new model. let's go to libraries and start collecting the components. Shall we start with building the circuit? First, we are going to build the single phase circuit. Okay, so we'll bring the capacitor later. From utilities, we need a solver, and we need a converter to convert the signals to simple Simulink signal. Probably we need two, one for the voltage and the other for the current. Now let's go and bring the other components. Can use multiplication. So basically we just need to change it to multiplication. We do need gain, a block. Can use this function. Instead of sine, use the inverse of cosine. Important component we'd like to have is the block that and calculate the active and reactive power. Which is this one. It's a crucial one. And then we'd like to have just to see if we can calculate these values in different way. The apparent power, we'll see in a minute. Alright, so if we need more components, we'll go back to library and bring them on. Okay, so basically the measured current and unmeasured voltage basically we can find the RMS value of the measured voltage and the RMS value of the current as well, in order to measure the apparent power. Simple as that. Alright, so this is the first method to do so. We can also measure the current and voltage to obtain the active and reactive. I think we've set the frequency to 50 Hz, so we need to adjust the frequency value. Okay, so the active and reactive power, we can calculate the apparent power by taking the square value of the active and reactive power, add them together, and then we have to have square root of that signal. So we have to go to the libraries and bring square root that function, right? So okay, so again we have the apparent power. In order to find the power factor, we can simply divide the active power by the apparent power, and the power factor will be obtained. We can also find theta by taking the inverse of a cosine theta, and we need to multiply that by 180 degrees and divide that by pi, because the angle theta okay, so theta here, it's in radian. We need to change it to degrees. Alright, so far so good. Now we use RMS values of the voltage and current to find the apparent power I need to change this one to 50. Probably very small. 200 volt. So let's go and update the values of the circuit, starting with the applied voltage. It requires the peak value. The RMS value is 200. So we multiplied it by the root mean square of 2. Frequency is 50 Hz, as shown in table number 1 presented early. Now for the resistance, so it's 10 ohm. The inductance is 0.318. I guess 1 second would be enough for the simulation time. Alright, so what do we have? So the active power is 39.9. Reactive power is very high, 395 volt ampere reactive. The apparent power, however, is 397, and we can see that the value of the apparent power measured using power block is equal to the value obtained by multiplying the RMS of the current and voltage. Before introducing capacitor, there is another way to find the RMS value. It's basically by trying to find the RMS value. So it's root mean square. So this is a square. You have to have an integral. And then we have to divide that by the simulation time. It's called the TS, taking the square root of that value should give us a value similar to obtained by the RMS block. Need to change this one to TS, and we need to do that for the voltage as well. Let's say that TS simulation time equal 1 second. Should have the parameter defined here in the workspace. Brilliant. I guess it's 1 over TS. So for the voltage, the obtained value is equal to the one obtained from the block, the RMS block. For the current, however, it's slightly different. So it's a little bit inaccurate. This inaccuracy came from that with the current there is starting current to charge the inductor, so it's a little bit higher than the rated value. In case of the voltage, we don't have this issue. Which means that this formation is only successful to measure and calculate the RMS value for uniform signals, such as a sine wave signal. Okay, so before introducing the capacitor, the reactive power was a bit high, consequently the apparent power is high, and the power factor is, I made a mistake. Yeah, so the power factor consequently is a bit low, and the angle between the voltage and the current, theta, is close to 90 degrees. When we introduce the capacitor, with the value calculated early, let's keep the series resistance with a very small value, or else the simulation will stop. We can see that the power factor is very close to unity. Theta is close to 0. The apparent power is reduced due to large reduction in the reactive power. So this is for single phase circuits. Right, so for the three-phase circuit, we're going to use components from the specialized technology. So basically we have two choices, either using series RLC branch or RLC load. So I'm going to use the branch since I know the resistance and inductance and even the capacitance of each element, and I will talk about the use of RLC load at the end of the presentation as well. For the sources, we can use either a three-phase source or three single-phase sources. So I'm going to choose a single-phase source. So based on table number 2, the voltage source of each phase is 240 RMS, or it's for the peak time it's 240 multiplied by the square root of 2. So phase A with the angle 0 degrees. Phase B, however, lagging by 120 degrees, and phase C is leading by 120 degrees. Right. For the measurement, can use one of the single phase components, either current or or voltage measurement, or we can use a three-phase volt ampere measurement. And with this one we have the choice either to make, I guess we need to make some room for the three-phase model. Okay, so we have two choices. It's either to let the measured voltage and current output with ports, so that we can wire that to scope or whatever place we want to take the signal to, or we can use labels basically for voltage, and we can name the label. So let's leave it with this form, and we can have the, so like that, and we can have the current measurement as well, and we even can have it in per unit, but in this case we need to have the base power and base voltage to calculate the per unit value. Brilliant. Now to receive this signal we need a block which is this one. So basically we need to name it with the same name we give to the voltage and current. And for the current as well, just like that. Input and output. So we need branch for each phase. And we can connect all of those maybe to the same reference as well, and shall have, okay, so phase A, phase B and phase C. With phase A we have a resistance and inductance. The resistance value, which we have written in table number 2, and the inductance as well. With phase B, so you can see that it changed, just omit the capacitance, since there is no capacitance in series with the resistance and inductance. So with phase B as well we have resistance and inductance only. Okay, so with phase C we have only a resistance, we have only a resistance, brilliant. So in order to calculate or extract the active and reactive power, we have to have a phasor, Of course, we do need the graphical user interface, and we'd like to have it on phaser, so let's change this. Should be just like that. Yeah, so we change it to phaser, and then we go back and change this one to auto again. Brilliant. Alright. Oh, sorry. With phaser we need to, need to change the frequency to 50 Hertz. Let's go back and change this again, so it can select the server automatically. Brilliant. So we do need a component to calculate the active and reactive power. So let's use both components and see exactly what is the difference. So one of the advantages of not having the wires directly from the measurement is that we can make it a little bit easier for the user to maneuver. So in order to show the output, I'm going to use a display. Plenty of them. Need to show the current. So the three-phase current. Would like to show the voltage as well. We do need to a user-defined function, which is this one. I'm going to explain why in a minute, but we also need to have a mixer like this one. Alright. So I'm going to use this user-defined function to find the power factor. So basically the function receives two signals. Let's say that the first signal is the active power. So let's name it as U1. And the second one is the reactive power. We can calculate the power factor by dividing the active power on the apparent power. Yeah, I guess that's right. So 3 for the 3 faces, and 1 extra for the one with the total. Alright, so we do need this one. We have 2 blocks. The first one, which is this one, can show us the active and reactive power of each phase. Well, this one is showing us the combined active and reactive power. So different blocks with different functions. We do need a demixer. With 3 outputs, 1 for each phase. So for phase A, phase B, and phase A, phase B, and phase C. Just like that. So the power factor for phase A, phase B, and phase C. So now let's test the circuit. Alright, so we do need to check to find out why those values are not as expected. So we need to change this to phase to ground. Brilliant. The power output per phase and the total as well. The power factor in each phase. Alright, so the second step is to introduce a capacitor with the value determined by table number 2. So we have a very small resistance. We have to have the resistance or else it won't work. Can you try that at home by yourself? So this is for phase A. Right. For phase B, a smaller capacitor, since the reactive power of phase B is only 500 volt ampere reactive, while it's in phase A it's 2000. Now we can see that the active power haven't been affected. However, the reactive power is almost gone to 0. The power factor is corrected to 1. And the total reactive power of the circuit is almost 0 as well. I've mentioned that we have two choices. It's either using the RLC branch or having the RLC load. So with load, it's a bit straightforward. Nominal voltage, frequency, we'd like to have 1000 active power and 2000 reactive power, inductive, and we can simply, let me show you exactly what I meant. Let me omit this one for now. Replace this one with the RLC load. Brilliant, and you can see that give us the same result. Now, if you would like to know how I've get these active and reactive power, I've actually set those values at the beginning and then worked out the value of the resistance and inductance. So these are the references cited in this presentation. So basically I'm assuming that phase A has 1000 watt and 2000 volt ampere reactive or VAR. The current, as we calculated early, a value of 9.3 ampere. We have the active and reactive power. In order to find the resistance and inductance, we can simply divide the active power by the current to find the value of the resistance and inductance, just like that. Alright, so with that we conclude this presentation. I hope it helps, and if you have been, thank you very much for watching. If you'd like to see more videos related to modeling and simulation of power system components, please subscribe to the channel and have a look in the description for the upcoming videos or lectures.